All right, welcome to our third lesson in the energy unit. Today we're talking about energy in springs. So our learning goal today, I can explain the different properties in springs and calculate the work and energy for a given spring. So the force exerted by an elastic device is proportional to the distance the spring has moved. What does that mean? Well, it means that we have a linear relationship. Linear relationship. All right. So below here, I just want to put together a diagram, and if you give yourself a bit of a sketch, this is what's happening when you stretch a spring. All right, so this is the force being applied to the spring. This is your extension of the spring. So as you pull the spring out, you get this relationship right here. Okay, that slope is what we call spring constant. So if I do right here, you can take an arrow way over here, slope calculates the spring constant. All right, so every spring has what we call a spring constant. It stretches the same amount. So we call it K, and it's your rise over run. It's your force divided by delta X. So that's how you calculate your spring constant. Now, for those that have been a little bit more adventurous with springs before, you'll know that once a spring reaches a certain point, it goes, all right, and it fails. And that's because you've unslunk a slinky, all right, you stretched it beyond the part where it can come back. So we call the region that's linear the elastic region. So that means that a spring will return back to its original shape in that elastic region. This region here is inelastic, which means that you have broken it or unwound a spring and it probably has failed. So you broke it. So that's your inelastic region. Now for us, we're only interested today and for this course in this elastic region. So we're going to stay within that area there. So at the bottom here, I have a couple definitions and equations. So I've given you the one equation in the red box. Here's the other one. Spring force is negative kx. So F is force applied to spring. All right, that's how much you're pulling on it. K is what we call the spring constant. It is the property of the spring. The tougher it is to stretch a spring, the higher the constant, and X is the amount of extension / compression, because you can squash a spring as well. All right, and below there I've got that already typed up for you. If X is greater than 0, that means you're stretching it, then the spring force wants to pull it back together. So that's why it's a negative value. So force is negative in that case. If you are squashing the spring, then force wants to push against you, and we assume push is a positive value. So if it's pulling, it's a negative value. If it's pushing, we have positive value. So there we are. So the energy stored in objects that are stretched, compressed, bent, or twisted is elastic potential energy. And if we look again at the graph, so I'm going to bring that graph forward. And again, we're only looking at the elastic region, so we're just going to draw the linear part of the line. So we're just looking at this region right here. This is true so this works for springs. It's true for elastics. Anything that you might twist, wind up, anything like that, this lesson, it works all the same. So we talked about the slope of that line is the spring constant. All right, so that's we already taken care of that. So M equals our K value, which is the spring constant. That's just rise over run, finding the slope. What does the area under the graph represent, though? Okay, so if you remember way back to our kinematics unit, we're finding the area under a graph, and we take the area under a velocity time graph, and that got us a position time graph. So what does the area under this graph give us? So if I was to find this value right there, what are we going to get? Well, let's take a quick peek here. So area equals 1/2 base times height. All right, it's just the area of a triangle. So 1/2. Our base is going to be delta x, and our height is going to be force. So that means we have 1/2 F delta x. Well, I know this is in newtons. I know delta x is in meters. Newtons times meters gives us joules. So area under graph, oops, giraffe, no, I don't know what I'm spelling there, graph, is work or energy. So am I going to have you finding the area under a curve or under the graph? Absolutely not. The whole point here was to determine that our spring energy is simply 1/2 F delta x. And there you go. You have a formula to determine your spring energy. And I can actually take it one step further. So we'll leave that as one version of the formula. And I can get rid of force, because on the previous page we talked about force is just K times delta x times delta x. When I clean that one up, we get 1/2 K delta x squared. So you have two potential formulas for spring energy. All right, so we have our force equation over here, and we have our energy equation down here. So an example, an apple of mass 1 kilogram is attached to a vertical spring with a force constant 9.6 newtons per meter. So spring constant or force constant, that is your K value as soon as you see that. All right. The apple is held so the spring is in equilibrium. So equilibrium means that if you have a spring, that's its natural rest position. So equilibrium, it's the natural rest position. Okay, so if it's an equilibrium, it would be if you just had it sitting there, that's how long it would be extended. So then we release it and it's allowed to fall, and what we're going to do is we're going to neglect the mass of the spring. So question A here, how much elastic potential energy is stored in the spring when it's fallen 11 centimeters? So what's happened is you've stretched the spring. Okay, so the situation here, we've stretched the spring. We've got that apple on the end. Because it's been stretched from its equilibrium position by 11 centimeters, it's stored energy. The spring wants to pull that apple up. So energy in the spring is equal to 1/2 K delta x squared. The only trick here is we got to make sure we work in metric or in SI units. So we do want to use 0.11 squared, not the 11. It's got to be in meters if you're doing these calculations. So when you do that calculation, 0.5 times the 9.6 times 0.11 squared equals 0.0, let's call it 6 joules of energy. All right, so that's how much energy is stored in that spring when it was extended that far, so not really that much. How much elastic potential energy is stored at maximum extension? So this spring, apparently the only elastic region is 25 centimeters. So if we stretch this spring right out to its max, how how much energy does it store? It's 9.6 times 0.25 squared. Punch that through the calculator. And we find that 0.3 joules is that maximum potential energy, because after 25 centimeters, it means my spring's going to break or bust. So there you go. Simple example there. And that finishes up any of the examples that I had set up here. So when you are going through the homework, you are probably going to need that formula there. So anytime a question is talking about calculate the force, determine the force, okay, that is the equation in question. As soon as you see a question that would like energy involved, you've got your two formulas for energy right there. And there you are. You're all set to deal with energy and springs. Good luck.